Everyone, and welcome to part C of number 2. We're looking at the top of page 26 here. Now, the instructions to this problem are on the previous page, so let me refresh your memory what they are. It's giving us a set, in this case, and asking us to determine whether or not that's a linearly independent set or not. The vector space that we're talking about is a set of functions. We saw this before in a previous example, so it's the set of functions with domain positive real numbers and codomain R. Okay, so we would start this problem the same way that we did the previous one by just forming a linear combination of our functions. So a sine squared x plus b sine squared of x plus c times 1 is equal to the zero vector. And again, that when we say zero vector in this particular vector space, we mean the zero function. Okay, and what's interesting about this example is that a very different strategy is going to turn out to work well here than what we did in the previous example where functions were involved. You might remember that last time we looked at something like this, okay, I'm going to do the same thing we did there and just give this equation a name. We used a strategy where we noticed that this is a statement that has to be true for all x in our domain, and use the fact that we can let x be any real number that we want to. Now, we could do that here, but it's easier to kind of think of this more in a global sense. Okay, so I'm wondering, and actually, before I get carried away, I just noticed a typo here, so I wrote sine twice. This should be cosine, obviously. Okay, let's fix that. Okay, so as I was saying, it's nice to think about this globally. So notice that there's a sine squared and a cosine squared in this equation. I'm wondering if you could maybe think back to trig for a minute here. And what's special about sine squared and cosine squared? You might remember a trig identity. In particular, when you add those two together, you get 1. Okay, and so what I'd like to do is to exploit that trig identity and say, let's choose a and b to be 1, just to get us started here. So a equal 1, b equal 1. That's going to make the first two terms in this equation star equal to sine squared plus cosine squared, which is going to give us 1. And here's my question to you. What would we need to make c equal to so that we get a 0 on the right-hand side? Well, if you think about it, we chose our a and our b so that this part that I'm underlining is equal to 1. So if we choose c to be equal to -1, the left-hand side should go to 0. Okay, so we'll let c be -1. If we do that, notice what happens. Okay, that means then, just kind of rewriting our equation, since a and b are both 1, we're just going to get sine squared x plus cosine squared x, and then c is 1, so we're going to get plus 1. Or I'm sorry, c is -1. Okay, back up. We're going to get a -1 there. And then we notice from the trig identity, sine squared plus cosine squared is 1, so we get 1 minus 1, and that gives us the 0 function. Okay, so what did we just show here? Well, we showed that equation star up here has a non-trivial solution right there. Okay, we chose an a, b, and a c, and not all of the a, b's, and c's are 0. Okay, so putting this into words, star has a non-trivial solution. Okay, and S is therefore linearly dependent. Okay, we are done with the problem here, but maybe just add one comment here. If S is really linearly dependent, there ought to be a dependence relation. Do you see a possible dependence relation here? Okay, it's really just kind of the equation that we just wrote down. The fact that when you take sine squared x plus cosine squared x, minus 1, you get 0. Okay, that's illustrating the interdependence of these three functions that we have.